In the last class, we discussed all about degrees of freedom. What is degrees of freedom? Degrees of freedom is the number of independent coordinates. So suppose a body in a dynamical motion, then we need only some independent coordinate to represent that motion of the system. Maybe there will be some unwanted coordinates. So what we are doing, we are removing the dependent coordinates and we are dealing only with independent coordinates. So the problem becomes less complex. Okay, and in some examples I told you the constraint forces will not do any work. So in this lecture, today's lecture, I will combine these two ideas, that is degrees of freedom, that is only independent coordinates is required to represent the dynamics of a system, and the constraint forces will not do any work. So we are going to discuss Lagrangian formulation in this class. Lagrangian formulation. And in this lecture, I construct the Lagranges equations from two basic principles. One is Alemberts Principle and other one is Hamilton's Principle. Hamilton's Principle of least action. Okay, the Alemberts Principle is based on some physical ideas, and the Hamilton Principle of least action is based on purely mathematical ideas. It uses the variation principle. Okay, so what is this Alemberts Principle? That is what I am going to discuss first. Alemberts Principle. What it is? Let us consider a system of particles. Suppose this is a ith particle in the system and a force Fi is acting on this particle. And there is a counter force, that is Pi dot, is acting in the opposite direction. And due to these forces, there is a small displacement. I call it as delta Ri. It is virtual displacement. So you know here the forces are acting in the opposite direction. So the system is in an equilibrium state. That is Fi vector minus Pi dot vector equal to 0. Now I am considering due to these forces there is a small work done, that is dw, and I write it as Fi vector minus Pi dot vector dot displacement vector is delta Ri, virtual displacement, equal to 0. And here this force may be a two type. One is actual force, that is Fia. This is actual force. And maybe it is a constraint forces, that is Fic. Okay, and this Pi dot, that is P equal to mv and P dot is mv dot, that is nothing but ma, right? Here what is this constraint forces? I tell you some examples. First example is a wedge. This is a wedge and a body is sliding over it. It is sliding here. So you can see the forces acting in between these two surfaces. So one force is acting on our wedge and other force is acting on our sliding body, right? So these two forces are equal and opposite and they will cancel out. And this force is what we call is normal reaction. And these forces will cancel each other. So here the Fic, there is constraint force minus Pi dot will be equal to 0. And another case, a simple pendulum. This is our simple pendulum and it is oscillating like this. So this length is constant we now, and it is oscillating. So here there are two forces, one is tension force and there is a counter force in this direction. Okay, so here also we can write Fi constant force minus Pi dot vector equal to 0. So in the most of the cases these constant forces will cancel out, and the work done by constant forces will be equal to 0. So the work done by constant force is automatically 0. So we don't want to consider this time, that is Fic time. So what we want to consider is only the actual force and the virtual displacement. So I can rewrite this equation as follows. That is Fi A minus Pi dot vector, so this is also vector, dot delta Ri equal to 0. Here I am considering a system of particles, so I am giving the summation I. Here you know Pi dot is nothing but mv dot, right? Here you can see this equation is analogous to Newton's second law of motion. But what is the difference? Here we avoided the constraint forces because constraint forces are very problematic. It is like we are avoiding some of our problematic peoples. Okay, similarly in dealing with the dynamics, these constraint forces are very problematic and we are going to avoid these constraint forces. No more these constraint forces will make our problems complicated. That is why we are formulating another mechanics, that is Lagrangian mechanics. Okay. Here I forgot to tell you one thing. This statement, the work done by constant forces equal to 0, is called the principle of virtual work. Okay, the principle of virtual work is work done by constant forces equal to 0. That is its statement or definition. The second one is Hamilton's principle of least action. Here we are introducing action integral S, that is equal to integral t1 to t2 L dt, where L is the Lagrangian. And in a dynamical system, the S should be extremum. Means delta S equal to 0. That is, delta is variation. Variation of action integral will be equal to 0. That is, we can rewrite this as delta integral L dt from t1 to t2 equal to 0. Based on this idea also, we can develop Lagrange's equation, that is d by dt dou L by dou qk dot minus dou L by dou qk equal to 0. From the Alemberts principle, we can formulate this Lagrange's equation, and from Hamilton's principle also we can formulate Lagrange's equation. But I told you, Alemberts principle is analogous to Newton's second law of motion. Here this Hamilton's principle of least action itself a fundamental principle. Okay. Now you people know the Alemberts principle, right? Now I am going to formulate Lagrange's equation from Alemberts principle. So I am considering a system of particles, that is n particle system, and I am considering this is my ith particle and this is the position vector of my ith particle, Ri vector, from some arbitrary reference point. So I can write this Ri vector equal to Ri vector, and this is a function of generalized coordinate q1, q2, q3, etc. qn and type. Here q are generalized coordinates. Okay, now I am going to find out the velocity, vi vector. What will be the velocity? We know v is equal to dr by dt. But there is a problem, we cannot directly take the dr by dt. Why? We know the Ri is a function of q1, q2, q3, etc. And we know q, the generalized coordinates, are a function of time. So we have to take partial derivatives. That is dou Ri by dou q1 into dou q1 by dou t plus dou Ri by dou q2 into dou q2 by dou t plus etc. etc. plus dou Ri by dou qn by dou t plus the last thing, that is dou Ri by dou t. Here I am calling this term as Ri dot. From now onwards, whenever I am taking a dot over a coordinate, it means it is time derivative of that coordinate. Okay, don't forget. And this one will be q1 dot, and I call this one as q2 dot and this one as q3 dot. Okay, so here you can see this is summation of many terms. So I can rewrite this equation by using the summation symbol, right? So what will be the vi vector? It will be equal to Ri dot equal to summation k equal to 1 to n, because we have n coordinates, into dou Ri vector by dou qk into qk dot plus the last term, that is dou r vector by dou t. So here this one qk dot is called the generalized velocity. That is the time derivative of generalized coordinate is called the generalized velocity. Next we discuss about virtual displacement. That is delta Ri, and we know this Ri is a function of q1, q2, q3, etc. qn. Okay, so what will be delta Ri? It will be equal to summation k equal to 1 to n dou Ri by dou qk into delta qk. And the important thing is it doesn't depend on time. Okay, so these are the assumptions we are taking. The virtual displacement doesn't depend on time. So the equation for virtual displacement delta Ri will be equal to summation k is equal to 1 to n dou Ri by dou qk delta q. Now we are going to consider the D'Alemberts principle for n particles. Right. I think you're remembering the equation, that is fi vector minus pi dot vector into delta Ri vector equal to 0. And here we are considering for n particles, so I am taking summation from I equal to 1 to n. So I can rewrite this equation as follows, that is summation I equal to 1 to n fi vector dot delta ri vector equal to summation I equal to 1 to n pi dot vector dot delta ri vector. So I am much interested in these two terms because we already know what is delta ri vector. So I am going to substitute for delta ri vector in this term. Okay. So that is summation I equal to 1 to n fi vector dot delta ri vector, that is summation k equal to 1 to n dou ri vector by dou qk into delta qk. Here fi vector and dou ri by dou qk are vector terms. So I am taking summation k equal to 1 to n summation I equal to 1 to capital N fi vector dot dou ri vector by dou qk into delta qk. Delta qk is scalar quantity, right? And this dot product of two vectors I call as gk. Okay. So what I got? I got summation k equal to 1 to n summation I equal to 1 to capital N. This term is gk into delta qk. And this term gk is called generalized force. And my question is, what will be the dimension of this generalized force? What will be the dimension of a generalized force? I think everybody know the dimension of a force, right? What is it? It is equal to ml t raised to minus 2. Whether this generalized force has the same dimension or not, that is my question. What do you think? Okay, I tell you. The dimension of generalized force sometimes will be equal to ml t raised to minus 2, but in general this is wrong. It is not. In some special cases, the dimension of generalized force can be ml t raised to minus 2, but in general we cannot say the generalized force has the same dimension as our force. But there is an interesting condition, that is product of generalized force into generalized coordinate. We are taking the product of generalized force and generalized coordinate, that is gk into qk. So what we get? Gk qk. And if you are taking the dimension of gk qk, then we get the dimension of work. This is always true. That is, the dimension of product of generalized force and generalized coordinate has always the dimension of work. So this is always true. So some examples I am telling here. First example. Here I am taking the force as generalized force. Then what will be the generalized coordinate? We know the product of this force and this generalized coordinate will be always dimension of work. Then what will be the generalized coordinate? It will be length. So what we get? Dimension of work, right? And another example, I am taking torque as my generalized force. Then what will be the generalized coordinate? We know the product of these two always has dimension of work. Then what will be the generalized coordinate here? It must be angle. Okay, these two are previous set questions. These are the previous set questions. The question is, a generalized force a factor on a system of particles, then F will always have the dimension of force. A, we cannot say this one, right? And F can sometimes have dimension of a force. That is what my first example. So this is the right answer. The second one, for a particular system, one of the generalized coordinate is an angle. What are the dimension of corresponding generalized force component? Yeah, this is my second example. That is torque is the right answer, right? Next is derivation of Lagrange's equation. Actually, I am not doing this derivation because we are dealing with MCQ questions. So this derivation will not help you. Memorizing the derivation, learning derivation will not help you. What you have to remember is the final equations. So we can derive the Lagrange's equation from Hamilton's principle or from Alemberts principle. Okay, so we get a Lagrange's equation. And this Lagrange's equations has two forms in two cases. First case is for a conservative system. For a conservative system, the Lagrange's equation of a conservative system will be d by dt of dou L by dou qk dot minus dou L by dou qk equal to 0. This will be the Lagrange's equation for a conservative system. And second case is non-conservative system. For a non-conservative system, the Lagrange's equation will be d by dt dou L by dou qk dot minus dou L by dou qk equal to gk prime, where this gk is called non-conservative force. One of the example for non-conservative force is friction. Here maybe you have a little doubt, what is this L? This L is called Lagrangian. And what is this Lagrangian? L is defined as L equal to T minus V, where T is the kinetic energy of the system and V is the potential energy of the system. So these are important equations. So don't forget L equal to T minus V and d by dt dou L by dou q dot minus dou L by dou qk equal to 0 for conservative system, and d by dt dou L by dou qk dot minus dou L by dou qk is equal to gk prime for non-conservative system. For the next two classes, we are playing with these two equations. So please don't forget. Okay. Next is superiority of Lagrangian over Newtonian mechanics. Why Lagrangian? That is the first question. Why we need a Lagrangian mechanics? Because we already know a mechanics that is Newtonian mechanics. Then why we need a new mechanics or new formulation of classical mechanics? Why? This is one of the fundamental question in physics. And if you are a student, physics student, you must ask these questions: why, what, and how. If you are asking these questions constantly, your understanding on the nature or understanding on the subject will constantly increase. So don't watch my classes passively. Try to ask questions yourself. When I am giving and when I am explaining some concepts, you please try to connect it with the other subject areas. That is, maybe I am discussing classical mechanics, so maybe something you heard in quantum mechanics related to this one. So try to correlate these two subjects. Maybe you can correlate with the electronics or statistical mechanics. Okay, so try to do these things. And if you have any doubts, then you do one thing, go to our website, there is a students area is given, there you can post your questions. Our faculty will engage with you and we will give you the answer, or mostly your friends itself come and give you the reply. So we can construct the knowledge as a community. So if you have any doubt, go to students area and post your doubts there. Okay. So the question is there, why Lagrangian? That is I am going to deal. Why Lagrangian? Because in Newtonian mechanics, what we are dealing with is force or momentum, etc. Right? You know, for force or momentum, it has directions and the magnitude. So these terms, these quantities are vector quantities, right? So in Newtonian mechanics, we deal with vector quantities, therefore it increases the complexity of the problem. Suppose a bead is moving on a ring, then you see here is velocity vector will be in this direction. When it is at this position, its velocity vector will be in this direction. Okay, even the magnitude is same, its direction is constantly changing. So it is difficult to deal the vector quantities. Another one is we can't avoid constraint forces. So what is this problem? So we have to take all the coordinates to solve a problem. And it is restricted to some coordinate systems. What are those? Cartesian coordinate system, polar coordinate system, spherical polar, etc. So we are dealing the problem in this coordinate system, Cartesian polar, spherical polar, or cylindrical coordinate system. Then what is the advantages of using a Lagrangian mechanics? So in Lagrangian, we define a term that is Lagrangian, it is L equal to T minus V. So in Lagrangian mechanics, we are dealing with the two quantities. One is kinetic energy and other is potential energy. And these terms don't have any direction. It is scalar quantities. And we are dealing with only independent coordinates. So here we don't want to take all the coordinates. We have to take only independent coordinates. So the number of coordinates will be reduced in a Lagrangian mechanics. So we have to deal with the only few number of coordinates. So the problem becomes very simple. And the coordinate system, we don't want to restrict it to Cartesian coordinate or polar coordinate or spherical polar coordinates in Lagrangian mechanics. We can take momentum as a coordinate. We can take length square as a coordinate. So these are possible in Lagrangian mechanics. And the equations of motion is invariant under coordinate transformation. In the coming class, we will discuss this coordinate transformation. Okay, don't worry. So you can see Lagrangian is more advantageous, right? But we are respectful to Newton. Why? Because Lagrangian is developed from Alemberts Principle, and Alemberts Principle is some special case of Newton's equations. So without these legends, Newton, Galileo, the science will not develop. Okay, so we must be respectful to those legends. Next is gauge invariance. Gauge invariance of Lagrangian. Here I am taking a Lagrangian. Lagrangian is it's L. and you know L equal to t minus b. And I am taking Lagrange's equation of motion. What is Lagrange's equation? That is equal to d by dt dou L by dou qk dot minus dou L by dou qk equal to 0. Don't forget this equation. It is very important. Okay. Now I am modifying my Lagrangian with a term. That is, with my Lagrangian I am adding a term, that is df by dt, where f is a function of q1, q2, q3, etc., qn and t. Right. Then my Lagrangian will be L prime. Now I am going to substitute this L prime in the position of L. That is what I get, d by dt dou L prime by dou qk dot minus dou L by dou qk equal to. So when doing this problem, here it is also L prime. When solving this problem, if we are getting this is equal to 0, then we call this function as gauge function. Okay, so if you are adding a term to Lagrangian and if you are solving the Lagrange's equation and we getting it is equal to 0, then that function we call as gauge function. This may be asked in set question or gate question. Maybe they will give some functions and ask you to find out which is the gauge function. So you have to substitute that function in Lagrange's equation, and for which function you are getting 0, then that will be the answer. Okay, so remember this one. And next we are going to discuss about symmetric properties and conservation laws. First I am taking space, and the space may be homogeneous or it may be isotropic. What is mean by homogeneity of space? The definition is like this: any point in space is equivalent to any other point of space. That means the space looks same. Suppose I am doing an experiment. I am taking two positive charges and now I am in Delhi. Okay, you know the two positive charges will repel, right? And I am doing this experiment in Mumbai. Here I am taking two positive charges. Here also these two positive charges will repel. It will not attract. By I am doing this translation, space translation, the law of physics will not change. So if I am doing this experiment at Delhi, it will repel, and if I am doing the same experiment in Mumbai, it will repel. That is, physics is never changes under translation. So that is the idea of this one. Space is homogeneous, right? And what is isotropic space? The definition is like this: the physical properties of system does not change for arbitrary rotation. That means the space looks same in every direction. And what is the consequence of these two symmetric properties? If space is homogeneous, then there will be a conservation law. That is, law of conservation of linear momentum. If space is homogeneous, then linear momentum will be conserved. And what is the consequence of this symmetric property? That is isotropic property. That is law of conservation of angular momentum. Okay, now I am taking type. and this time may be homogeneous. What it means? At the time of Newton, we know F is equal to ma, and now also we are using the same equation, that is F equal to ma. So physics is not changed by time translation. It's at time of Newton. Even now also this equation is valid, and this property, this symmetric property, leads to a conservation law, that is law of conservation of energy. Now this is a previous set question. So here I think you got the answer, right? So I am moving to another topic. Now I am going to discuss about generalized coordinates. So for a system of particles like this one, and it is some generalized coordinate system, and this is my ith particle, and the position vector is Ri vector. So I can write this Ri vector equal to Ri vector is a function of generalized coordinate. I am taking these two R as a generalized coordinate. So the generalized coordinates are q1, q2, etc., qn. And here generalized coordinates. Here, you know, these generalized coordinates are our independent coordinates. And the number of independent coordinates will be equal to degrees of freedom of that particular system. Suppose now I am giving you some Lagrangians, then can you find out the generalized coordinates? That's my question. So identification of generalized coordinates. I am taking first example, that is my L is equal to half m x dot square plus y dot square plus z dot square minus v, because we know L is equal to t minus v. Here what are the generalized coordinates? I am telling you here x is a generalized coordinate, y is a generalized coordinate, and z is a generalized coordinate. So x, y, z are generalized coordinate here. Second example, I am giving you L equal to half m r dot square plus r square theta dot square minus v. Here what are the generalized coordinates? Here I am telling this one and this one are the generalized coordinates. And one more example, that is L equal to 1 by 2 m r dot square plus r square sine square theta phi dot square minus v. Here what are the generalized coordinates? This one and this one, that is r and phi. And theta is not a generalized coordinate here. Okay, maybe you've identified the property, that is generalized coordinate have dot, right? This one have dot, this one have dot, and all this have dots. So here you maybe find out that generalized coordinates are those coordinates which have a dot, right? Why that? Because we are interested in dynamics of a system. Dynamics is the motion of a system. So system is in motion means it's changing with respect to time. Its coordinates are changing with respect to time. So suppose a coordinate, I am taking r coordinate, it is changing with the time. Then there will be a velocity, that is r dot. Okay, so here it is generalized velocity. So these are the coordinates which changes with respect to its motion, and all other terms are constant. That is, here you see the r is changing with the time. So we are taking that as generalized coordinate, and phi is changing with the time. So we are taking it as generalized coordinate, and theta is not changing with the time. So it is not representing the dynamics of the system. So here the independent coordinates are only r and phi. Okay. Here I took Ri equal to Ri of Q1, Q2, Q3, etc. Qn. Then what will be the generalized velocity? That is V I vector, that is equal to dri vector by dt. So here we want to take the partial derivative, that is dou ri by dou q1 by dou t plus dou ri by dou q2 by dou t plus etc plus last coordinate, that is dou ri by dou qn by dou t. I already done this earlier, right? So we can write this as q1 dot, this as q2 dot, this as qn dot. So we can rewrite this equation as vi vector equal to summation k dou ri by dou qk into qk dot, right? This is the generalized velocity. Now you know about velocity, right? Then what will be the generalized kinetic energy? I think you know the equation of kinetic energy is equal to half m v square, right? I am taking a system of particle, that is I am taking I and mi vi square. Here I am rewriting this equation for less confusion, that is 1 by 2 half mi vj dot vk. So here I am going to substitute this value here and here. So what we get? We get t equal to summation I 1 by 2 mi into vj, that is summation j dou ri by dou qj dot summation k dou ri by dou qk dot. Here these are vectors, that is ri, these are vectors, and the qj dot and qk dot are scalars. So I am rewriting this equation, that is summation I 1 by 2 mi into summation j summation k dou ri vector by dou qj dot dou ri vector by dou qk into qj dot qk dot. And this term, I am calling this term as ajk. So I can rewrite this equation as follows, that is t equal to summation I 1 by 2 mi into summation jk ajk qj dot qk dot. So this is the generalized kinetic energy. Kinetic energy in different coordinate systems. First I am taking Cartesian coordinate system. This is very much familiar to everyone. So this is my Cartesian coordinate system, x, y, z. And I am considering a particle of certain mass m, and it is moving with some velocity v. Okay, so the position of this particle can be represented by x, y, z coordinate. Now I am going to find out its kinetic energy, that is kinetic energy, that is equal to T equal to half m v square. So this is a v is a velocity vector. It may have component in x direction, y direction, and z direction. So I can write I vx plus j vy plus k vz. These are the unit vectors. So what will be the v square? So I have to multiply this with the dot product with the another I vx plus j vy plus k vz. So what we get? We get vx square plus vy square plus vz square. That is vx is dx by dt all square plus dy by dt all square plus dz by dt all square. This is nothing but x dot square plus y dot square plus z dot square. Okay, so we get the kinetic energy equal to half m into v square, that is x dot square plus y dot square plus z dot square. So this is the kinetic energy in Cartesian coordinate system. Then what will be the kinetic energy in cylindrical coordinates? That is rho theta z. Okay, we know the kinetic energy equal to half m v square, that is x dot square plus y dot square plus z dot square. So if we know x dot, y dot and z dot in cylindrical coordinate, we can find out the kinetic energy, right? First I am considering our Cartesian coordinates, that is x, y and z. X, y, z. Okay, and this Cartesian coordinate system, suppose there is a particular this position and I can draw a position vector r vector like this one. Okay, so this r vector as a projection over xy plane like this one, and I call this projection as rho, and you can see there is an angle between these two, that is I call as theta, and the projection of this point over z axis I call z. Okay, so here you see the projection over x axis, we can call it as rho cos theta. So we got x equal to rho cos theta. Next, the projection on y axis is rho sin theta. So we got y is equal to rho sin theta, and z is z itself, right? Z is equal to z. Now we are going to find out dot product of these values. So first I am taking x dot. You see here there are two components, one is rho and one is cos theta. So first I am taking rho, derivative of rho, then I take derivative of cos theta. Okay, so rho dot cos theta minus rho sin theta theta dot. Derivative of cos theta is minus sin theta, and we are taking it the time derivative, so we get theta dot also. And what is be y dot? Y dot will be equal to rho dot sin theta plus rho cos theta theta dot, and z dot will be equal to z dot itself. Now we have to find out square of these functions, that is x dot square. What is x dot square? That is rho dot cos theta minus rho theta dot sin theta all square. That's equal to rho dot square cos square theta minus 2 rho dot rho theta dot cos theta sin theta plus rho square theta dot square sin square theta. Next, what is y dot square? It is equal to rho dot sin theta plus rho theta dot cos theta all square. That is equal to rho dot square sin square theta plus 2 rho theta dot sin theta cos theta plus rho square theta dot square cos square theta, and z dot square equal to z dot square is z. Now we have to substitute in the equation of kinetic energy, that is T is equal to half m x dot square plus y dot square plus z dot square, right? So what we get? T equal to 1 by 2 m into x dot square plus y dot square. See here rho square is a common term, and we can take cos square theta plus sin square theta, and here this term and this term are opposite, that is this is plus and this is minus, so these two terms will cancel, and here also rho square theta dot is common, and we can take sin square theta plus cos square theta. So what we get? It is equal to 1 by 2 m into rho dot square into sin square theta plus cos square theta plus rho square theta dot square into sin square theta plus cos square theta plus z dot square. Okay, here you know this value is equal to 1 and this value also equal to 1. So what we get? Finally we get T is equal to 1 by 2 m into rho dot square plus rho square theta dot square plus z dot square. This is an important result. Okay, don't forget this one, because if some problem has a cylindrical symmetry, then we directly use this equation. So don't forget these equations, these are very important. Then what will be the kinetic energy in spherical polar coordinates? That is r theta phi. We know the kinetic energy T is equal to half m x dot square plus y dot square plus z dot square. So we have to find out what is x, y and z in spherical polar coordinates. Okay, so I am considering our x, y, z coordinate system, Cartesian coordinate system. X, y, z. And this is our r vector. And I am taking this angle as theta. Okay, so this have a projection our xy plane. So this length will be equal to r sin theta, right? Because it's the opposite side. Okay, this is the side. So this length will be equal to r sin theta, and I am taking this angle as phi. So what will be the projection of this one over x-axis? It will be r sin theta cos phi. Similarly, its projection on y-axis will be r sin theta sin phi. So we got x equal to r sin theta cos phi and y is equal to r sin theta sin phi. And what is z? Z is equal to r cos theta, right? That is z is equal to r cos theta. Now we have to find out x dot, y dot and the z dot. So x dot will be equal to dr by dt into sin theta cos phi plus r d by dt of sin theta cos phi plus r sin theta d by dt cos phi, right? And the y dot will be equal to, similarly, you have to find out y dot and you have to find out z dot. Then find out x dot square plus y dot square plus z dot square. Then multiply it with the half m. So you get kinetic energy. This is a work for you. Okay. Don't worry, I will tell you the final result. Finally, you get T equal to 1 by 2m r dot square plus r square theta dot square plus r square sine square theta phi dot square. So this will be the final answer, that is kinetic energy in spherical polar coordinate system. So do all these derivations and verify whether the given equation is correct or wrong. Okay. Here I am concluding all the ideas. So first I am taking small displacement. So the small displacement in Cartesian coordinate system, that is ds vector. In Cartesian coordinate system, it will be dx I cap plus dy j cap plus dz k cap. And in cylindrical coordinates, ds vector will be equal to d rho cap plus rho d phi cap plus dz z cap. And in spherical polar coordinate system, ds vector will be equal to dr r cap plus r d theta theta cap plus r sin theta d phi cap. And what will be the corresponding velocity? So first in Cartesian, the velocity, that is v vector, we know it is ds by dt. So what we get, it is x dot I cap plus y dot j cap plus z dot k cap, right? And what will be in cylindrical coordinate system? V vector will be equal to ds by dt, that is equal to rho dot rho cap plus rho phi dot phi cap plus z dot z cap. And what will be in spherical polar coordinate system? V vector will be equal to r dot r cap plus r theta dot theta cap plus r sin theta phi dot phi cap. Then what will be the kinetic energy? First one, in Cartesian, the kinetic energy T will be equal to 1 by 2m x dot square plus y dot square plus z dot square. And in cylindrical coordinates, T will be equal to 1 by 2m rho dot square plus rho square phi dot square plus z dot square. And in spherical polar coordinate system, T will be equal to 1 by 2m into r dot square plus r square theta dot square plus r square sine square theta phi dot square. Okay, so please remember all those equations, especially don't forget equations of kinetic energy in these three coordinates. It's very, very important. If you remember these equations, Paka, then you can solve many problems just by looking the diagram. Okay, so don't forget, this is very important. The first thing in Lagrangian mechanics is we have to find out the Lagrangian, represented by L, and we know L is equal to T minus V, where T is the kinetic energy. So when we are going to solve a problem, first we have to find out the kinetic energy. In most of the problem, the potential is given. Maybe in some problem we have to find out the potential from given conditions. So to solve any problem, first we have to find out kinetic energy. And this general equation to find out kinetic energy is half m x dot square plus y dot square plus z dot square. And there is a tricky method. If you have some imagination, then we can solve the problems by superposition method. Here we are adding the velocities. So this is the easiest way or tricky way of solving the problem, but it requires some amount of logics and imagination. Initially we solved the problem using the general equation, then we start to use the trick. Okay, first I will tell you how we can solve the problem by using the general form, and then I will tell you how we can use the tricks. And you know, L equal to T minus V, and in Cartesian coordinate system, L is equal to half m x dot square plus y dot square plus z dot square minus v. And in cylindrical coordinate system, L is equal to half m rho dot square plus rho square phi dot square plus z dot square minus v. And spherical polar coordinate system, L equal to half m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus v. And in polar coordinate system, it will be L is equal to half m r dot square plus r square theta dot square minus v. So this is the difference between spherical and polar. Okay, so this term will not be there in the polar coordinates. And I already told you the Lagrange's equation of motion. It is d by dt dou L by dou q dot minus dou L by dou q equal to 0. And this is for a particular case, that is for conservative forces. Here I am considering an example and taking the Lagrangian in Cartesian coordinate system, that is half m x dot square plus y dot square plus z dot square minus v of x. Here my potential is a function of x. Okay, so you see here there are three generalized coordinates, that is x, y and z. Okay, I told you how we can find out the generalized coordinate. For a generalized coordinate, it have a dot over it, right? So first we are taking the x coordinate, that is d by dt dou L by, here the q is x, that is dou x dot minus dou L by dou x equal to 0. So what is dou L by dou x? We have to find out it, right? So d by dt of dou L by dou x dot. So the derivative of x dot is 2x dot. So we get m x dot minus dou L by dou x. So here there is no x term, so partial derivative of this one with respect to x will be 0. But here this function has x. So what we get? Plus dou v by dou x equal to 0. That is equal to mx double dot plus dou v by dou x equal to 0. Now I am considering the another coordinate, that is y coordinate. Then what will be the equation of motion? D by dt dou L by dou y dot minus dou L by dou y equal to 0. That is equal to d by dt of derivative dou L by dou y dot, that is m y dot, minus dou L by dou y. So here there is no y term, and here also there is no y term. So it is equal to 0, equal to 0. So we get my double dot equal to 0. Similarly, you have to find out for z. It's a work for you. Okay. Another example. I am taking plane polar coordinates, that is r theta, and we know the Lagrangian in plane polar, that is 1 by 2 m r dot square plus r square theta dot square minus b. So now we have to find out the equations of motion. So here what are the generalized coordinates? R and theta. Okay, so first we are taking the r, that is the corresponding equation of motion is d by dt dou L by dou r dot minus dou L by dou r equal to 0. That is d by dt of dou L by dou r dot. See, that is equal to m r dot minus dou L by dou r. Here it is r is there, so we get m r theta dot square. And suppose this v is a function of r only, then we get an additional term, that is plus dou v by dou r equal to 0. Okay, that is m r double dot minus m r theta dot square plus dou v of r by dou r equal to 0. This is the equation of motion. Now we are taking the another coordinate, that is theta. So the corresponding equation of motion will be d by dt dou L by dou theta dot minus dou L by dou theta equal to 0. So what we get? D by dt of dou L by dou theta dot. So here theta dot is there, so what we get? We get m r square theta dot minus dou L by dou theta. So there is no theta term, right? So it will be equal to 0. That is equal to 0. So what we get? Here you should be careful. You have to take derivative of r and the theta dot also. Okay. So what we get? We get m r square theta double dot plus, we are taking the derivative of r. So what we get? 2r r dot, that is 2m r dot theta dot equal to 0. Okay. Now work for you. Find Lagrange's equation of motion. For the following Lagrangians. First one, I am taking spherical coordinate system. So in spherical coordinate system, we know L is equal to 1 by 2 m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus v. I am taking this v as a function of theta. Okay, and second one, cylindrical coordinates. So in cylindrical coordinate system, L will be equal to 1 by 2 m rho dot square plus rho square phi dot square plus z dot square. And here my v is a function of rho, phi and z. So please find out Lagrange's equation of motion. So first you have to identify what are the generalized coordinates. These are the generalized coordinate for this problem and these are the generalized coordinate for this problem. Okay, so do it. Here this is a previous net problem. It is a part B problem. Okay, so what is the question? The equation of motion of a system described by the time dependent Lagrangian is, so the Lagrangian is given and we have to find out the equation of motion of the system. So the Lagrangian is L is equal to e raised to gamma t into 1 by 2 m x dot square minus v of x. This is equal to 1 by 2 m x dot square e raised to gamma t minus v of x e raised to gamma t. Okay, just elaborated this equation. Now what is our equation of motion? That is d by dt dou L by dou q dot. Here what is q? The generalized coordinate is x, that is dou x dot minus dou L by dou x equal to 0. So first I am going to evaluate this dou L by dou x dot, that is dou L by dou x dot equal to what we will get. X dot is here only, so we get m x dot e raised to gamma t. And what we get for dou L by dou x? It is equal to, so here this term has x term. So we get minus e raised to gamma t dou v of x by dou x. Now we have to take d by dt of dou L by dou x dot, that is m x dot e raised to gamma t. Here x dot is a function of t and e raised to gamma t is also function of t. So we take m and the time derivative of x dot is x double dot e raised to gamma t plus x dot time derivative of e raised to gamma t, that is gamma e raised to gamma t. Okay, now we are substituting these two values in this equation, that is dou L by dou x dot equal to m x double dot e raised to gamma t plus m x dot gamma e raised to gamma t minus dou L by dou x, that is plus dou v by dou x e raised to gamma t equal to 0. So here e raised to gamma t is a common term. So what we get, m x double dot plus m x dot gamma plus dou v by dou x into e raised to gamma t equal to 0. So here m x double dot plus m x dot gamma plus dou v by dou x equal to 0. So this is the answer. So the option A is the right answer. Okay. This one is a previous net problem. It is a part B problem. The question is to find out the kinetic energy of the pendulum. So it is a double pendulum and I am going to redraw this diagram. So the diagram is like this. There is a support and a pendulum of length L is suspended. Length is L and mass is m. And another pendulum is attached to it. It has mass m and length L. And from this axis, vertical axis, the angle is taken as theta 1, and from this vertical axis this angle is taken as theta 2. What they asked to find out? That is kinetic energy. We know kinetic energy is equal to half m x dot square plus y dot square plus z dot square. But there is no z coordinate. Okay, so we are taking only x dot square plus y dot square. Okay, here you can see there is one particle and there is another particle. Two particles are there. So this equation will be summation I equal to 1 to 2 half mi yi, right? So the kinetic energy equal to 1 by 2. We are taking the first mass, that is mass m, and its coordinates I am taking as x1 dot square plus y1 dot square. So this is the x1 coordinate and this is y1 coordinate. Okay, and another particle. This is second particle. So for this second particle I am taking this distance as its x2 and this distance as its y2. Okay, that is half m x2 dot square plus y2 dot square. Now what is x1 value? We have to find out x1 value, y1 value, x2 value and the y2 value. So what is the x1 value? So this is the x1 value. Okay, so this is theta 1 and this length is L. Then x1 will be equal to L sin theta 1, right? And what will be the y1 value? This is the y1 value, and that will be equal to L cos theta 1. Okay, we got it. Now what is x2? Here this is the x2 and this length is, we know it is x1. So x2 will be equal to x1 plus this length. This length is L sin theta 2. That is x1 plus L sin theta 2. We already know the x1 value. So this is L sin theta 1 plus L sin theta 2. Now what is y2? This is y2 and this much length is, we already know, that is y1. So y2 is equal to y1 plus this distance. What is this distance? This is equal to L cos theta 2. That is y1 plus L cos theta 2. Here we know the y1 value. The y1 is equal to L cos theta 1 plus L cos theta 2. Now the problem is over. You just take the x1 dot, y1 dot, x2 dot, y2 dot and just take its squares and add it. So this is a simple work. So I give this as a work for you. The correct option is option B and you please try to recheck this option. Okay. Maybe you have to revise some of your plus 2 mathematics textbook. Then only you can include this cos theta 1 minus theta 2 times. So please revise your plus 2 mathematics and please write down the necessary equations related to addition of angle and subtraction of angle and all. Okay. I think this much is sufficient for today. Okay, then do all the given works and see you. Bye bye.